let us continue our statement. So, neural net universality theorem, or why neural nets can compute any function. So, considering a function on which depends on one variable x, we can construct the neural net which perfectly can calculate the value of the function f of x for any range x. Usually we normalize the values of x, the values of argument from 0 to 1, but it is not restricting because we can renormalize our domain of variable, and also we can also normalize. We can normalize also the values of our function. So the last fact was the spline approximation of our function, which is sigma minus 1 applied to f of x, and to calculate this function. And the response of our network will be perfectly the value of our function in the point x when the value x is input value of our neural net. So now I think very interesting fact that how it can extend on many input variables. So we can now consider more dimension case. And as usually we construct multi-dimensional case, we begin from two-dimensional case. Once we elaborate mathematical formalism of two-dimensional case, we can pass to any dimensional case, and theoretically nothing constrains us to extend it to infinite dimension. For example, for some physical problem, it is important, for example, working in Fock space and so on. So now we start with two input values, x and y. And we also construct some function on two variables, which is well defined, and which so how to construct our neural net, which give us the values of the function on two variables, x and y. So we have initially such configuration of our neural net. So the x and y are input values, and let us define some corresponding weights W1 and W2, and the corresponding bias P on the neuron. So let us now we bring one of the weights to 0 and consider only one weight and one variable, of course x, and we annulate the second variable. So we consider only one-dimensional case. So, and what happened in one dimension? So we prescribe to x the weight coefficient 11, and to y annulating coefficient 0. Yes, so it vanishes, and we have only the reply in one direction. Yes, 11x minus 6. 11x minus 6. So fixing the first weight W and the bias B, now this one can see how they affect out from the neuron. So what happened? You see, we have some three-dimensional figure, which is something like sigmoidal, but with increasing the bias, with increasing the weight coefficient, it tends to be vertical. So, yes, tends to be vertical. So in ideal, if we put enough big weight coefficient, we can arbitrarily put it as we want, but should be very, very big value. And the second, we annulating mean value equal to 0. So we have some step function. Now the three-dimensional step function. Yes. So this step, if we consider, for example, Sx minus b divided by W1, it means this Sx. We can regulate the position of vertical increasing of this step. Yes, it is 0.25. Then we can change, for example, minus b by W1. So W1 is about 1000. So we should choose the corresponding b. So in the manner that Sx is 0.5. Yes. So since we can consider our figure from 0 to 1, yes, in both dimensions, x and y, and also the height is will be some height, but normally it should be 1 initially. Okay, so we can regulate the position of begin of jump of our step function 3-dimensional. The same thing we can organize when we bring to 0 W1, the first weight coefficient, and let us put now W2 equal to 1000. So we have also vertical step function, but with position from depend on y. So y is the coordinate of our vertical step beginning. So we also can choose 0.25, 0.5, 0.7 by the same formula. Yes, Sx is equal minus b divided by W2. Now W2, W1 is equal. So we have in this direction step function and in this direction the step function. What will happen after? The number of the neuron is again the step point, and this is so we have in X direction and in Y direction. Now we should construct the bump three-dimensional function like in one-dimensional case. So how we do it? So we add two step function. Okay, two step functions. One step with the weight h, and the second with minus h, with weight minus h respectively. So we have, you see, for example, this figure, what does it mean? It is our step, our bump, begin on the point, in the point 0, 3, like x coordinate, 0, 3, then reach to 1, then remain constant, and then at 0, 6, 7, it decrease to 0, and from 0, 7 to 1, it will be 0, 0. And so we have kindness of this bump figure is 1. We can construct, for example, also this highness of this 0.75, or we can move some point of the beginning of our step function in the sense that begin at 0.4 and finish at 0.7, and also the highness is 1. More in detail, how it is, how it can be arranged. So return to the step function. So we have x, y. Then x is the jump coordinate by x equal to 0.50, and output is our, so it reach 1 and remain. So we assume that the weight on x input has some 1000, some large number, and the weight W2 is 0, as we told. So we have the step function in this. So similarly, we can put the weight 1 equal to 0, weight 2 is equal to 1000. Yes, for almost vertical direction of our jump function, so step function, and so we have here x, y, and the coordinate of jump by x is 0.50. So in the similar way, we have y, jump y, coordinate 0.50. We have only definition of this function from 0 to 1. So it's a half of our possible range with jump. But it is not strictly, we can arrange it in all the range of 0, 1. We can use the step function, and we have just constructed to compute a three-dimensional bump function. To do this, we use two neurons. Now we leave the weights not 0, both, and every of these weight contributes to the bump function. So here the bump should be 2 steps, yes, 2 glued steps. So it is illustrated in this diagram. So x, for example, 0, 30, it is begin to jump, yes, to begin with vertical, 0, 30. Then we reach the highness. It is 0,6, and this highness is defined by the weight from the hidden neuron to the output neuron. And the same thing, if we want to return to 0, we should annulate this highness. So should prescribe the weight coefficient of the second neuron minus 0,6. So we return to 0 by this figure. So we have glued combined two step function. So we can regulate as beginning of jump, or also as the end of jump and the highness of this bump figure. So now we can do it in the second direction. So in this situation, bump function, we annulate y by the weight 0. So we consider only x, and it is in the direction x. We have the evolution of our step function, so bump in the direction x. The second, the same thing we can do for the direction y. So to do it, we prescribe the weight from x to both hidden neurons equal to 0. So we have only the influence of the value y. And for example, we prescribe here y 0,30, you see, by combination of again, by combination of minus b divided by w, 1 or 2 depends on which direction we construct this bump function. Okay. So, and also the highness is 0,6, so we should prescribe from first hidden and from the second hidden neuron the weights 0,6 and minus 0,6. So we have begin from 0. On 0,30 we jump up to 0,6 our times. Then we move to 0,70, and then we put down our figure up to 0. So we created our three-dimensional bump function. So we can vary this parameter to construct any function from 0 to 1. From 0 to 1, like the domain of definition, yes, the domain of the parameter, argument definition. But the value of function can be the constant of any highness and depend on the ways which we prescribe to these connections. Okay, so we can we have this. Now we should combine both in both directions, x and y. And what happens? Happens the following. If we add to this our bump function, yes, 1, 0, 30, 0, 70, 0, 30, 0, 70, and here let's divide. X begin to on 0, 40 and end to 0, 0, 60, and the second y 0, 30 and 0, 70 by the highness 0, 30. Okay, 0, 3. So we have such function, you see? We have this cross type 2 bump function with the highness 0, 30, but up on their intersection, we have the highness 0, 60, the double, because it's one and other. So two highness are added. And we have such some base, yes, cross base, and some tower upper. So, what is our scope? Our scope is to build something like a tower function. And this tower function will be precisely rectangle approximation of our three-dimensional function. Yes, and it is our aim. How can we do it? How can we cut the base of this tower? We should cut the base of this tower because it is extra construction which break our game to approximation of our three-dimensional function. So we shall see it how it's possible to do. So once we can construct with the begin and end of this tower, yes, by axis x, and by axis y of some predetermined height. So we can then have any function approximate in this case by some many towers function. So now our aim is to cut the base, the cross like base. So and how can we make the tower function? To do this, we can use special training procedure using neurons to exclude, execute, and if then else procedures. So in the following mode, if the combined output from the hidden neurons, yes, so we verify the output from hidden neurons. If it is bigger or equal to threshold, some threshold, output 1, else output 0. And combining some parameters, which parameter? Threshold should be put to the value to the value of 3h divided by 2. So in this situation, we could squash a plateau. The plateau is this cross-like base. Yes, the plateau. So we could squash this plateau to 0, down to 0. Yes, by this procedure, because we are forcing to in this if then else we squash our base to 0. So in this situation, you see, we can, for example, construct the network of the following topology. So X then 040, 060. Yes, it is jump up and jump down. And then this 15, 0, 15, 0. So by X we jump on the highest of 15, 0, 15, 0, and then to down to 15, minus 15, 0. And the same we do for Y. Yes, it begin jump on 0, 13 of the Y coordinates and jump down at 0, 7. So we have squashed to the base to 0, and we have the pure tower function. The pure tower function. So our ideal rectangle. So it is this parallelogram in our 3D. So now how to glue two networks together to calculate two different tower functions? Very simple. We consider two blocks, two models of our network, network 1 and network 2. Network 1 is responsible for the first tower. And it perfectly annulate, squash the base, yes, cross base for the first tower. So we can easily, in this situation, to construct a neural net. To construct a neural net, which you see by x begin 0, 1 and end 0, 2, and by y coordinate 0, 8 and 0, 9. So we have the first tower. Yes, first tower. So this tower corresponds to this model, to this first upper model. And the second tower is the same thing. You see, it is begins 0, 7 and ends 0, 8, and then by y 0, 2 and ends 0, 3. So we have the second tower, which corresponds to it. So the first okay. So the same idea allows us to calculate as many towers as we like. So by simple adding the models, yes, the models x, y, and some models, we can add several towers. We can make them arbitrarily thin and high. So we control like highness is also the thickness by x and by y coordinates. So we have the possibility in this situation to construct many towers construction which can approximate the function. So, in particular, by making the weighted output from the second hidden layer, a good approximation to sigma minus 1f, we ensure the output from our network will be good approximation to any desired function f. So we have the same thing as before. So we apply the inverse of our activation function sigma is to the function f. So at the end, of the output of our network, the output neuron of our network, we obtain the desired function f up to the approximation, tower approximation, which we have arranged. And such approximation can be done with any grade of precision we want. Now consider three variables, x1, x2, and x3. We add some three variables. The following network can be used to compute the tower function in 4 dimensions. So we have x1, it is begin and s1, t1, yes, begin and end the tower. x2, s2, t2, begin and the second tower. x3, begin and end the third tower. So here the x1, x2, x3 denote the input of the network S1 and S2 and so on are step point for neurons, yes? So we have step point of the step functions. That is the weights in the first layer are very big, of course, to have the vertical comportment of the function growth. And biases are assigned so that step points are equal to S1, T1, S2, T2, and so on, which how we have 3 towers. The weights in the second layer alternate plus minus h, because we should jump and then return, where h is some very large number. The output bias is minus 5h divided by 2 for 3-dimensional argument of our function. The network calculates a function equal to 1 under 3 conditions. x1 is so we cut off our plateau, our gross type space. x1 is between S1 and T1. x2 is between S2 and T2, and x3 is between S3 and T3, and will annulate to 0 level or to squash all the bases. This is a tower where 1 is a small area of entrance space and 0 is everything else. By gluing together many such networks, we can get as many towers as we like. So approximate an arbitrary function of 3 variables. The same idea works in m dimensions. So only what change in m dimensions? Only the output bias, not more minus, for example, 5h, but minus m plus 1, 2. Yes, minus m plus 1 second. H is changed to properly insert the desired values and remove the plateau. So if then else is the standard procedure to cut off our plateau configuration. Now let us say several words about some activation functions, not sigmoid. And it can be because we can find of some function more correspondingly adequate to our learning procedures. For example, if we have some necessity to take into account some range of values and to ignorate and to prescribe a small priority to some other values. It can be. So it can be arise on some empirical motivation. So we have seen that the neural networks made up of sigmoid neurons can compute any function. So it's very good. And the sigmoid function is very important function because it is very smooth. It begins on 0 and finishes on 1. So it's a very good function. But it is very interesting also to bring this function to the jump function and then to approximate any function by jump. So something like we construct the integral subset. Recall that in a sigmoid neuron, the inputs x1, x2, and so on result the output sigma of weighted sum of our neurons values, the previous neuron values, plus our bias. Okay, so Wj is our weights and B is the bias. And sigma is sigmoid function. 1 divided by 1 plus exponential minus x minus z. Sigma of z minus z. So we have sigmoidal function. Very interesting. I would like to repeat that. Very interesting that this function is very similar, like shape, to the distribution function of Gaussian distribution. Yes. So its derivative, for example, will be very similar to the probabilistic density of the Gaussian or normal probabilistic distribution. Consider absolutely arbitrary activation function. let's so we had sigma is sigmoidal function, but let's consider some function also monotonic, no, not monotonic, some mean monotonic, yes, so-called average monotonic function from 0 to 1, for example. But it varied in some strange manner and some arbitrary manner. What can we do with such activation function? So we have activation function, and we assume that our neurons has inputs x1, x2, and so on, with the weights w, w1, w2, and so on, and bias b. So we should construct this weighted sum plus bias, and then to take our function in this final point, this activation, neuron activity. So in this situation, our neuron is not more sigma neuron, but neuron with some activation function S. Just as with the sigmoidal function, there is a possibility to become a very good approximation to a step function. So we can also make the same reasoning, changing the bias by very big value. We can obtain again a step jump function. So by changing the bias, one can see that we can set the position of the step to be wherever we choose, but under some conditions which are very important. So we use the same trick as before we compute any desired function. What is the property should be of the function s of z to be a valid function for activation properties? First of all, this function should be well defined as z tends to minus infinity and z tends to plus infinity. So we not it randomly. We have designed such shape, but it begins on from 0 on minus infinity and finish on +1 on plus infinity. So it is something like the function sigmoidal. So these two limits that, because the value on minus infinity is the beginning of our step function, and the zeta s on the plus infinity will define the highest, yes, the second extreme of our step function. So, for example, not possible that there are two values equal between them, because in this situation we should have a banal, a trivial constant step function without step, without jump. Okay. But having these properties, neuron based on such activation function are universal for computation. So we can prescribe sigma, not sigma, but S new our activation function. Yes. For example, having our activation function, having the some value, yes, from 0 to 1. You see, again, we have some function which begin at almost 0, yes, at 0, and to 1 at for x equal to 1. So we especially have taken some activation function in this manner. So we have this activation function, you see, this activation function, like the output from our output level. Trying to rise up the weight, we obtain, you see, even if W equal to 100 is rising from 6 to 100, we can see that we have not jump, but very near to jump growth. So the step function, a pretty good approximation, but not an approximation, because this one is not vertical. This one is not vertical, but it is nothing no matter, because we can put some weight as big as we want. So this window of growth can be very small. It is hard. It is with as small as we want. So it can be invisible by eye. So we can reach vertical configuration, but we can proceed as before with calculation of any function. So suppose that we want our network to compute some function f. As before, we can do it trying to design our network so that the weighted output from our hidden layer is sigma minus 1 f of x. So we take sigma minus 1 of our function, and we can do, using the technique described before, we can use the hidden neurons to produce a sequence of one function, and we can approximate our function by a series of rectangles. So I think for today I will not expose new material. Perhaps tomorrow will be other person. And so let's finish properly. So, so we finish. Now do registration. The registration. Here, yes. Perfetto. Adesso, the
verify